This is a quick recap of chapter Units and Measurement. First is physical quantities. All those quantities which can be measured directly or indirectly and in terms of which the laws of physics can be expressed are called physical quantities. Physical unit. A standard amount of a physical quantity chosen to measure the physical quantity of the same kinds. Same kind is called a physical unit. Measurement of a physical unit is equals to numerical value of the quantity and to size of the unit is equals to nu. Now second is a relationship between numerical value and size of unit. The numerical value n of a physical quantity is inversely proportional to the size of unit. N is inversely proportional to 1 upon u. Okay, or we can say nu is equals to a constant, or we can say n1 u1 is equals to n2 u2. Now fundamental quantities, the physical quantities which can be treated as independent of other physical quantities and are not usually defined in terms of other physical quantities are called fundamental quantities. The 7 fundamental quantities are mass, length, time, electric current, temperature, luminous intensity, and amount of substance. Now, derived quantities. The physical quantities whose defining operations are based on the other physical quantities are called derived quantities. Derived units. All other units which can be expressed in terms of physical quantity, fundamental units are called derived units. Now, fundamental units. The physical units which can neither be derived from one another nor they can be further resolved into more simpler units are called fundamental units. The units of length, mass, time, etc. are fundamental units. Okay. So now, system of units. There are 4 systems of units: CGS, FPS, MKS, and SI system. A complete set of units which is used for measuring all kinds of fundamental and derived quantities is called a system of units, CGS, or the metric system. In this system, the fundamental units of length, mass, and time are centimeter, gram, and second, respectively. In FPS or British system, in this system, the fundamental units of length, mass, and time are foot, pound, and second, respectively. The MKS system. In this system, the fundamental units of length, mass, and time are meter, kilogram, and second, respectively. SI. SI is the abbreviation for System International des Units, which is a French equivalent for International System of Units. In this system, the fundamental units of length, mass, time, electric current, temperature, luminous intensity, and amount of substance are meter, kilogram, second, ampere, Kelvin, candela, and mole, respectively. The 7 basic SI units. First is meter. Second is kilogram. Third is second. Fourth is ampere, and Kelvin, candela, mole. 2 supplementary SI units. First is radian. It is defined as the plane angle subtended at the center of a circle by an arc equal in length to the radius of the circle. Theta is equals to arc upon radius is equals to L by R. And second is steradian. It is the solid angle subtended at the center of a sphere by a surface of the sphere equal in area to that of a square, having each side equal to the radius of the sphere, which is equals to surface area upon radius square. Now, coherent system. A coherent system of units is a system based on a certain set of fundamental units from which all derived units are obtained by multiplication or division without introducing any numerical factor. Now, next is advantages of SI. It is a metric, rational, coherent, and internationally acceptable system of units which covers all branches of physics. Now, order of magnitude. The order of magnitude of a physical quantity is that power of 10 which is closest to its magnitude. To determine the order of uh, magnitude of a number n, we can express it as n is equals to n into 10 to the power x. If n is between 0.5 and 5, then x will be the order of magnitude of n. Annual parallax. It is the angle theta at which the semi-major axis of the Earth's orbit perpendicular to the star's direction is seen from the star. Now next is molar volume. 1 mole of every gas occupies a volume of 22.4 liters at STP. This is called molar volume of the gas. It contains an Avogadro number n is equals to 6.23 into 10 to the power 23 molecules. Next is mass. The mass of a body is the quantity of matter contained in it. The SI unit is kg. Next is weight. The weight of a body is the force with which a body is attracted towards the center of Earth. W is equals to mg. Inertial mass. The mass of a body which determines its inertia in translatory motion is called its inertial mass. It is measured from Newton's second law of motion. Mi is equals to, which is inertial mass is equals to force upon A. Next is gravitational mass. The mass of a body which determines the gravitational pull upon it due to the Earth is called its gravitational mass. It is measured by Newton's law of gravitation. The formula is mg is equals to f r square upon gm. Dimensions of the derived quantities. These are the power to which the fundamental units of mass, length, and time must be raised in order to represent a derived quantity completely. Next is dimensional formula. It is an expression which shows how and which of the fundamental units of mass, length, and time occur in the derived unit of a physical quantity. Now, dimensional equation. The equation which expresses a physical quantity in terms of fundamental units of mass, length, and time is called dimensional equation. Principle of homogeneity of dimensions. This principle states that a physical equation will be dimensionally correct if the dimensions of all the terms occurring on both sides of the equation are same. Now, uses of dimensional equation. First is to convert a physical quantity from one system of units to another. Suppose a physical quantity has a dimensional formula m raised to the power, let me write here, m raised to the power a, L raised to the power b, and t raised to the power c. Let n1 and n2 be its numerical values when the units are u1 and u2. n1 u1 is equals to n2 u2, and n2 will be equals to n1 m1 upon m2 raised to the power a, L1 upon L2 raised to the power b, T1 upon T2 raised to the power c. Now, second use of dimensional equation is to check the correctness of a given physical relation. Third use is to derive a relationship between different physical quantities. Next is significant figures. The significant figures are normally those digits in a measured quantity which are known reliably plus one additional digit that is uncertain. Now, rules for counting the new number of system figures in a measured quantity. First is all non-zero digits are significant. Second rule is all zeros between two non-zero digits are significant. Third is all zeros to the right of a non-zero digit but to the left of an understood decimal point are not significant. But such zeros are significant if they come from a measurement. Fourth is all zeros to the right of a non-zero digit but for the left of a decimal point are significant. For example, 648700 has 6 significant figures. Okay, so now fifth rule is all zeros to the right of a decimal point are significant. Sixth is all zeros to the right of a decimal point but to the left of a non-zero digit are not significant. A single zero conventionally placed to the left of the decimal point is not significant. Seventh and last is the number of significant figures does not depend on the system of units. Now, significant figures in the sum or difference of two numbers. In addition or subtraction, the result should be reported to the same number of the decimal places as that of the number with minimum number of decimal places. Significant figures in the product or quotient of two numbers. In multiplication or division, the result should be reported to the same number of significant figures as that of the number with minimum of significant figures. Now, rules for rounding of a measurement. First is if the digit to be dropped is less than 5, then the preceding digit is left unchanged. Second, if the digit to be dropped is greater than 5, then the preceding digit is increased by 1. Third, if the digit to be dropped is 5 followed by non-zero digits, then the preceding digit is increased by 1. Fourth, if the digit to be dropped is 5, then the preceding digit is left unchanged if it is even. And fifth rule is if the digit to be dropped is 5, then the preceding digit is increased by 1 if it is odd. Now, accuracy and precision of a measurement. Accuracy refers to the closeness of a measurement to the true value of physical quantity. Precision refers to the resolution or the limit to which the quantity is measured. Now, error in measurement. It is the difference between the measured value and the true value of a physical quantity. It gives an indication of the limits within which the true value may lie. Elimination of random error. The errors which occur irregularly and at random in magnitude and direction are called random errors. To eliminate the random errors, a large number of readings are taken and their arithmetic mean is taken as the true value. Is equals to a1 plus a2 plus up to an divided by n, and which can be written as 1 upon n summation I is equals to 1 to n ai. And now absolute error. The magnitude of the difference between the true value and the measured value is called absolute error. Such errors are given by is equals to elimination of random error minus a2. And similarly for absolute error, a3 is equals to a minus a3. Okay, and in general we can say is equals to minus an. Now, mean absolute error. The arithmetic mean of the positive magnitude of all the absolute error is called mean absolute error. Is equals to plus up to which can be written as 1 upon n summation I is equals to 1 to n I. Now, relative error. It is the ratio of the mean absolute error to the true value. Now, percentage error. The relative error expressed in percent is called percentage error. Percentage error is equals to upon A into 100%. Now, error combination in a sum or a difference. When two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors associated with the individual quantities. Z is equals to this plus B. Now, error combination in a product or a question. When two quantities are multiplied or divided, the fractional error in the final result is the sum of the fractional errors of the two quantities. We can write this as on Z is to del on A plus P upon B. Now, error due to the power of a measured quantity. The fractional error in the nth power of a quantity is equal to n times the fractional error in the quantity itself. If z is equals to a to the power n, then del z upon z is equals to n del a upon a. Now, general rule. If z is equals to a to the power p, b to the power q upon c to the power r, then the maximum fractional or relative error in z will be p into this plus q into this plus r into and percentage error in z will be equals to del z upon z into 100, which will be equals to p del a upon a into 100 plus q p upon b into 100 plus r into 100. Now, propagation or combination of errors.